met him only a couple of weeks ago under the most bizarre circumstance, which ended him swimming in the nude in the ride. Then I fell off the chair when he walked into the Vizier conference because I didn't know he was a fit.
So you met before the Vizier conference?
Before the Vizier conference, and talking about sort of, it should come up, just give it time.
Would anyone like to just fiddle with my machine?
Not me. I'm not good at fiddling.
Just says slideshow.
Wait.
Here it comes.
Good.
There you are.
Okay, there we are.
Alex is going to talk to us
On this subject.
on the information retention in water. Alex, it's all yours.
Thank you. Please note what I haven't called this talk. I haven't called it water memory. Homeopathy talks a lot about how you manage to get something into water when you've infinitely diluted the chemical in it. But the term water memory is so controversial that I shall not use the term in this talk. But what I want to show you is that there is a highly unusual and highly plausible way that information can be retained in water. And it was actually suggested by the great Indian engineer working somewhere in Pennsylvania. I think it was at the University of Pittsburgh, if I remember rightly, called Rustom Roy, who died back in 2010 or 11. And it's often used to explain homeopathy. So what I shall present to you is how the possibility of retaining information in water emerges from the quantum entropy of water polymolecules. And this is something which no one has considered. People have talked about the polymolecules. They've mostly said that they can't form stable states, so you don't have to worry about them. They're all formed by individual water molecules connected by hydrogen bonds. There's been a huge amount of work done at South Bank University, and you can find under South Bank University enormously beautiful pictures of polymolecules of water. But this, roughly speaking, is what I'm going to tell you. Firstly, of course, according to conventional theory, you can't have anything memorized in water because it doesn't retain any kind of digital information. Fine. Rustom Roy suggested that it depends on the structure of water, in particular the polymolecule structure, and he published a paper way back when about this, sometime like 2008 or 9. Then I just want to make the point that water polymolecules are immensely rich and complex. And also, that if you look at the entropy, and we know that entropy is connected to the concept of information, there are two ways one usually defines the entropy of a system. The classical macroscopic entropy, which is its usual definition of an integral over heat content, and a microscopic entropy, which is usually considered to be a quantum entropy. And the quantum entropy is a sum over microscopic states. Now, of course, Boltzmann was the first person who related the two entropies together, made himself so unpopular that he got depressed and committed suicide. A great loss, unfortunately, because the idea that you can understand the entropy according to a sum over microscopic states, as of course the connection between statistical mechanics and statistical thermodynamics, and one of the foundations of modern physics, and used in quantum statistical mechanics and quantum statistical thermodynamics, and it goes all the way down the line. Now you can extend what I'm saying to you today into quantum statistical thermodynamics in a little more detail to study the dynamics of the whole process. I'm not going to do it. I'm just going to leave it very simple. It's almost totally conceptual, this talk, but the basic realization is that water's quantum entropy is far too large. There are far too many polymolecule states. So if you were to form a quantum entropy which was summed over all the polymolecule states, you'd get far too large an entropy. This means that water cannot explore all its polymolecule states. It just gets, the entropy saturates, as I've called it, entropy saturation. The entropy saturates and you just get stuck, caused by well, this is my thesis, right? The entropy gets stuck. It can't explore all the polymolecule states, so you get left with a macroscopic sample of water, and if you put a little bit of something into it, iron, it explores a few more polymolecule states. If you put magnesium into it, it explores a few more polymolecule states, but those polymolecule states will be different from the iron and from the magnesium, or whatever it is, iodine or alcohol. So it looks as if the water information in this form actually retains some kind of memory of what you put into it to create a particular selection of polymolecule states. The entropy saturates, information is retained. I've told you more than I should have done there. That's meant to be part of the end. Section 1. Well, I've told you. Most people equate information with digital information. Digital information, or even quantum information. But you need solid structures which are stable, which are not fluctuating in many different ways. And as long as you have a system where the microscopic structure is all at 6s and 7s, and the hydrogen bonds are rearranging and reforming themselves, you can't retain a stable form of information, which is digital information. So everyone has always said to crazy people like homeopaths and Benveniste and others, you just can't get water to there to be any kind of memory in water. It's just impossible, they say, because you can't retain a normal digital kind of information. Deduction. Water cannot retain information. Information retention, memory, in water is impossible. So the question, is this deduction valid? India's celebrated engineer, Rustom Roy, who was a fellow of the foreign fellow of the Royal Society and many other great distinctions, said water memory may depend on its microstructure. He wrote a paper with Iris Bell and two other fairly I was going to say dubious, but I don't think it's fair to call them dubious characters. They're people who are quite happy to stick their neck out. And the paper they wrote wasn't very well received. But water memory may depend on its microstructure. It cannot depend on chemical content, but hydrogen bonds link to form water polymolecules. They link water molecules, and the H2O molecules thus form water polymolecules. how can this help? They effectively suggested this, but they didn't give an answer that satisfied anyone. So a possible solution via this structure of water is to say that the water polymolecules contain far more possible kinds than water can explore. Can these structural possibilities affect the deduction we made previously? The previous deduction being that the water memory may depend on its microstructure, line 2 in this slide. The water polymolecules are immensely rich and complex. I'm going to go through this quantitatively in the vaguest terms. Contain far more possibilities than can be explored. In what sense could such structural possibilities contain information? There are unexplored possibilities. That doesn't sound very much like information, but I shall try and persuade you that it might be considered information. The entropy of water can be calculated in two different ways. The usual way is to consider the macroscopic entropy, heat entropy, and then there's the microscopic entropy. The macroscopic entropy is classical. It's what the people who worked out entropy, Clausius and company in the mid-19th century, worked out. It's all to do with the integral of the heat change over temperature. The microscopic entropy is to do with the microscopic states, and usually it's calculated as a quantum entropy, and in this case it will depend on the water polymolecules. So the normal macroscopic entropy, we have two different entropies, the macroscopic entropy and the microscopic entropy due to polymolecules, and I'm going to show you that the entropy from the polymolecules is much too large. There's far too many of them. Okay, so the normal macroscopic entropy I'm calling S sub h, and it's calculated according to the change in heat content with the classical equation which was written as the first definition of entropy. You say the increase of the heat entropy is the increase of heat dQ divided by temperature. I don't teach thermodynamics at the minute, so I have to look all these things up very carefully and make sure I haven't screwed up by mistake. So you integrate over increasing temperature, and you find that you integrate from absolute zero to temperature T, and you get this nice little integral. So it's well defined, and it can be calculated easily enough, and you can calculate the heat content of water entirely according to your thermodynamic measurements. But now the microscopic entropy, S sub P, I call it, due to polymolecules, is the sum, this is the classical way of putting it, the entropy is equal to the information. It's the same as the information. Sigma over all possibilities I of the probability of that possibility times the log of the probability, where, as I've written it out, sigma over I is the sum over all, in this case, polymolecules, and the probability I is the probability of occurrence of the ith polymolecule. Now, the polymolecules go up to hundreds of water molecules in a polymolecule. You can join each polymolecule, you can join each water molecule practically to any previous water molecule in the polymolecule. So you get, for a water polymolecule of n molecules, for n plus 1 polymolecules, you can add your water in n plus 1 in n places. So you begin to develop a number of polymolecules, a number of polymolecules which is of the order of n factorial,
Isn't it then factorial cubed?
Well,
squared, because you have a
well, you can do that too, yes, all right, but I didn't want to complicate matters. I'm just drawing them out.
Very big.
It's a big number,
Okay.
yes.
If you can show me that rigorously,
I can.
I'll add your name to the paper.
As an acknowledgement only.
Okay, thank you.
Thank you.
Anyway, so Pi is the probability of occurrence of the ith polymolecule. Well, I didn't have time to write this all out, I'm afraid, but the first one must equal to the other one. There are far too many polymolecules, so the two entropies of water must be equal. The macroscopic entropy must equal the microscopic polymolecule entropy. Therefore, water samples cannot explore all the polymolecules. The number of polymolecules becomes limited. This limitation represents a kind of information. Now, when Fisher discovered and proposed the concept of Fisher information, is because when you have a statistical distribution over a given domain, the distribution only concentrates the sample into a particular region of the domain. So, roughly speaking, the width of the domain divided by the standard deviation, or twice the standard deviation, gives you a certain measure of the limitation. And if you take, I think you take the log of that to get some kind of information equivalent to an entropy. So this limitation represents a kind of information analogous, because it's a limitation on a statistical distribution, it's analogous to a Fisher information. So I'm proposing that our limitation, bottom line here, the limitation is a quantum form of Fisher information. And I'm offering for criticism the name quantum Fisher information. Conclusions. Quantum entropy saturates. The difference between the quantum and the classical information is a form of information available in the liquid. And this information is retained in liquid water. What kind of information? It's a quantum analogue of Fisher information, which I propose calling quantum Fisher information. Shall I say what I've said?
Yes.
The conventional theory, review of 6 sections. The introduction. The conventional theory says you can't retain digital information in water. Therefore, information in water is impossible, liquid water. Rustum-Rai suggested that it depends on the structure of water. 3. Water molecules, polymolecules, are immensely rich and complex. The vast numbers were investigated at South Bank University and available on their website. There are 2 entropies that you can define for water: a macroscopic entropy, which is the usual entropy, a microscopic quantum entropy. The 2 have to be equal, but water's quantum entropy is potentially far too large. The conclusion is that the quantum entropy saturates. It gets moved to an upper bound, limited by an upper bound, which is equal to the macroscopic entropy, and you get enormous numbers of polymolecules which are not explored in the quantum entropy of water, any given sample of water. Information is retained in liquid water. Conclusion. Now, I do want to add one thing to this. Homeopaths tell us that above about 70 degrees centigrade, you cannot prepare a homeopathic preparation. There's an upper temperature limit to what you can do. This suggests that once you get up to 70 degrees centigrade, you can actually accommodate all the water polymolecules. So I have no way yet of calculating the actual temperature at which the saturation fails, but the suggestion is that the virtue of this particular explanation for water memory is that it tells us that there will be an upper limit to the temperature at which water memory works, and it might be possible to calculate predictively from the information in South Bank University files that that value is, roughly speaking, 70 degrees centigrade. Now that is very hopeful and wishful thinking, but it does tell us that this form of entropy saturation, for the reason that information is retained in water, has a good chance of being shown to, a possible chance of being shown to be quantitatively correct, and it seems to have qualitatively some rather attractive behaviour. Okay, now I've said my bit. Thank you. Thank you, Anton. Am I within the time limit?
Yes, you're more than in the time limit. We could have given you some of your time, not put under such pressure. But we have time for questions.
Well, first of all, a comment. The reason I think qualitatively, and it can be made rigorous, that it's n factorial squared is that you're dealing with a three-dimensional system. So if you think about a molecule as having a surface, that means you have a two-dimensional set of surfaces. If you think about water as being a banana, you can imagine sticking the banana in different orientations, absolutely, which are distinguished linearly independently by being at 90 degrees to one another, hence the square. So what you do is you form something which is some shape in 3D, and hence the square.
Yes, and you'll probably like to say that some of those oxygen atoms have got 4 hydrogen bonds round them.
Yes, effectively.
So they won't be able to be added to. So
resonance and coherence, that's right. So you might reduce it.
Speaking,
yes,
if it grows like a blob, then it's n to the 2/3 or something.
That's
that
correct.
Got to play with.
But in fact, that's a very small part of the thing.
If you'd like to play with it with me,
I don't think you need to
for any number of little games.
I don't think you need to think about the 2/3 because that's such a small number compared to the square that you can pretty much neglect it.
Yes.
But on the other hand, some other comments. I have seen something like this before, and I've been racking my brains as to the person.
Oh well, if you can show it to me, I'll be so happy because the two Russian ladies.
I know where he lives, and I've got his address. I just need to look it up.
The 2 Russian ladies at the last conference had written about coherence domains in water,
oh, that's interesting.
and it's definitely true that if you lower the entropy all across it, you will have a kind of coherence. So I want to study what they've done in great detail.
Let me say something else about coherence. In quantum theory of growth, so you're thinking about, we were considering, or I looked at a problem many years ago now, 25 years ago, we were trying to improve the mobility in gallium, in two-dimensional electron gas systems. And we had a session at a pub, at which we considered how the quantum process of growth took place and how to smooth the domain boundary. As you're growing, it's MBE, you're growing atomic layer by atomic layer, and we had an idea how to do that. We tried it, and it gave us a factor of 10 improvement in mobility, which was pretty cool. And it comes from, again, what's happening as something's trying to grow is there's really a resonance going on in there, and that resonance is introducing a symmetry. Now, I think it's perfectly possible that if one puts something into water, that the water takes on that shape, as it were, in 3D, and that's retained.
Absolutely, that's right.
But
and when you dilute it, for some reason, it retains a lot of that
it's
information. Can we have another question or two? Yes, sir.
In your investigations, have you come across the work at Washington University and a guy called Jerry Pollock?
General Pollock?
Yeah.
Yes, I'm sending my paper to Jerry Pollock's journal, Water. And Jerry Pollock gave an absolutely stunningly brilliant talk at the Water and Homeopathy Conference in London. How long ago was it?
I don't know. I wasn't there. You came swimming off.
And he runs an annual conference called WaterCon, which is this year in...
Yes, but what he's doing with his structured water, phase 4 water, is different from this. This is a conceptually completely
I'm not
different...
sure that's a good leap, because they, the Watercom people, led by Jerry, believe that the fourth phase of water, to use his phrase,
Is what?
to use his phrase, fourth phase of water, only exists in living systems, which ties up with the previous
Oh,
comment.
but he showed that the fourth phase of water occurs in test tubes and in all sorts of places. He gave some absolutely fantastic and fascinating discussions of it at that conference at the Royal Society of Medicine down on Wigmore Street.
Well, having attended several of these conferences, there are, as usual, different, as it were, directions of thought, and the strong loop is that the fourth phase of water is necessary for living systems.
Correct. That way round. Yes.
Yes.
Petri
Okay,
dishes and
sorry,
articles
you've
and
got
all.
more people wanting to ask questions.
So
Madam?
if you're not in possession of it, I recommend you have a look at the fourth phase of water. Yeah.
Yes, I will. You had a question? You put your
Yes.
hand up.
Relative to water storing information relative to living systems, it's my understanding that one of your primary goals is to integrate Vedic principles into natural science. So would you say, assume that the Vedic principle interacting with water is non-local, and that the 70-degree limit has to do with some interaction between thermodynamics and...
Well, what I didn't mention at all in this, and I have written in a review, which I forget whether I published it, is that most religious systems believe that you can, as it were, charge water by transferring subtle energies from your hands into water. You can hold a phial of test tube or whatever it is of water, and that the water then becomes valuable. It retains something of the subtle energy of the person who blessed it. But that's, I mean, it's probably in the Mormon tradition as well. It's probably in most religious traditions. It's certainly in the Christian tradition.
We can physically transfer
that
information,
is-
but we don't talk about water.
That, I consider this a scientific meeting. I didn't want to get involved in such esoteric questions.
Well, we have an A in
They're,
the title
they're
of
closely,
natural philosophy.
yes, they're closely related, and I investigate such questions myself constantly. Yes, ma'am.
I think it's important to be aware that science and spirituality are coexistent.
Oh, absolutely, I do. I promote.
Our histories from the Epiphany philosophers, who were, that was their concern, was how...
Which philosophers?
The Epiphany philosophers in Cambridge. This is, we're talking, I don't know, 30 years or so
More
ago.
now, nearly 50 now.
Whenever, I don't know, it's before my time, but that was the idea, was that how can we see the relationship between spirituality and science?
Well, I'm going to a congress in the city of Pune, I think it is, August 25th and 26th, and I've been asked to give a major talk about the relationship of science and spirituality.
Exactly.
And it is actually one of my, I confess to all present, it's one of my major interests. And I've been a teacher of meditation since 1973. And the first instruction I was given when I joined Maharishi Mahesh Yogi's university was to work out the relationship between the Western sciences, which are scientific, and the Eastern sciences, which are, quote, spiritual, in some vague sense, right? And that's been a work and a major interest of 45 years. And if you want the simple answer is this. The spiritual sciences of the East believe in two or more levels of reality. The gross level, which we see with our senses and hear and touch and see and taste and smell, which they call gross. But they maintain that underneath the gross level there is a subtle level of reality which controls the gross. And when they do their forms of either Chinese medicine, working on the qi energies, yang qi and yin qi, which the Indians call prana and shakti, or the Indians work with their Ayurvedic system of medicine, and that works on subtle controlling forces. They're working at a subtle energy level. These systems can cure chronic diseases. They do so constantly, and the Western journals don't like writing up their papers terribly much. But they do, and we have many journals on Ayurveda medicine, Ayurveda integrative medicine, Chinese medicine, and a lot of my students in India have researched these things in considerable detail. So we work on the scientific side, the spiritual side. We're trying to do the brain waves of people in deep meditation to a greater degree of accuracy. They've been done deeply at Maharishi University of Management in Iowa in the United States. But these are hugely, I think, important frontiers of scientific research, which people who follow scientism write the most dreadful things about and banish to the depths.
Well, so my history is that I've been practicing Vedic sounding for... Vedic sounding. Sounding. I'll be talking, I'm going to be talking about the mathematics of the Maheshwara. So the Maheshwara Sutra, exactly, and which was what my teacher suggested I do, because Alain Danielou, whom you probably know, is he was a great Vedic scholar, and he hinted that the Maheshwara is the key to mathematics, and so that's one of the things I've been working on. So I think we could certainly talk some more about this, because this is very
Let's talk about it in detail.
We can talk about that
later. There was one more.
Yeah. Your analysis depends on the existence of polymolecules in water. So first of all, have you got any scientific evidence as to their existence? Can you show that you've got long chains of high molecular weight pieces of water, or is it speculation?
What? Could I share? Did you say?
You're saying that water retains information by having combinations of polymolecules of water.
Do you understand how homeopaths prepare homeopathic medicine?
Yes, I do, yes.
They
do
some very strange things.
6 centennial dilution, yes.
They dilute it 10 to the 40 times,
yeah.
or
yeah.
20 C.
Yes, I know this, but do you have any
evidence? And you get something which apparently has an action on an organism.
I understand the entire basis.
I wrote a basic mechanism of that in the Journal of Alternative and Complementary Medicine in 2003.
I understand homeopathy, and I'm not opposed to it. I just want a simple answer to the question, which is, have you any scientific evidence for the existence of polymolecules of water?
That's all in Southbank. Southbank has generated a huge amount of evidence for the existence of polymolecules in water.
Okay, fine.
Okay?
Yeah.
And I ought to be expert on it,
yeah,
but
yeah.
I'm a bit vague about it,
Right.
so I'll go and gen up.
Okay. So the reason I ask this is because I personally synthesised polymolecules myself 12 years ago by striking an arc. Striking an electric arc between carbon electrodes underwater. I've personally synthesised polymolecules. So I've created very ultra high molecular weight gas in my garage, which burns. And essentially, what I did was I repeated exactly Ruggiero Santilli's similar experiment that was documented on the internet a dozen years ago. Now, the interesting point. So what I'm saying is that I've got personal evidence of the creation, personally, of polymolecules. So you're suggesting the existence of polymolecules of water. So what I've got is circumstantial evidence to support your point of view. So I'd be very interested to learn more about scientific work that you're doing in that field.
That's another thing I'd like to discuss with you afterwards. That would be very interesting.
Yeah.
Because there are other things that are said to happen when you put very high voltages between carbon electrodes underwater, and there can another phenomenon as well. So I'd very much like to know what you find.
Have you told Santilli about this?
Well, no, and the reason for that is because these molecules are called polyvines, and 12 years ago you could Google polyvines and find all about Ruggero Santilli's work. Now, you can Google polyvines, but you'll find greenhouses, plastic pots, polythene tunnels.
But I know Santilli well. I could.
Yeah. Oh, yeah.
I know him very well. So if you could, if you want to tell him about it, there's no problem.
Well, yeah, and my presentation on Thursday is another repeat of Santilli's work.
Well, if you've got these repeats of his work, he would be very interested. So
Is
you
there
can
any-
mention me in the
any-
context if you write it.
Any other?
Yeah.
Yes.
Well, given what both Mike and Nicola were talking about, I must profess to a huge amount of ignorance here. But in Dutch, there's a saying which is ongehinderd door enige kennis, which means unhindered by any knowledge. I'd like to make a comment about the fourth state of water, because I don't really believe in the fourth state of water. Fourth phase. I don't believe in it just thinking about it. But I think that what is clear is if one moves to systems which are very small, so one moves to nanosystems in which water is embedded, then such things as the freezing point of water go way up, and also the structure of water in such systems can be formed by that nanostructure that one's making. So I would then say there's a fourth phase, a fifth phase, an nth phase, an infinite phase of water, because as one changes that structure, the water is going to take on that, or take on aspects of that structure, and it's also going to change its physical characteristics, because it's not confined to just being water anymore. It's water which is moving out quantum mechanically into the system which it's encased inside. So
Jerry Pollock
yes.
gave 7 lines of evidence for a particular form of the fourth phase of water.
Yes. Okay.
And he essentially said that, water normally crystallizes into something like a diamond's structure, where the oxygen atoms have a coordination number of 4 through hydrogen bonds with other oxygen atoms. And these give you 6-membered rings, which are chair-shaped, roughly speaking, chair-shaped. 6-membered rings. Cyclohexane you can call that. 6-membered ring, which is either boat-shaped or chair-shaped. And he showed that in the fourth phase of water, these things expel a whole series of protons. They become negatively charged, and they become benzene, graphene shapes. You get flat hexane ring sheets of the water molecules, which expelled a certain number of protons to the outside, and you can show that there is a change in structure from the X-ray crystallography. You can show that there's a change in charge content. You can show that the water adjacent to it has gone acid because of the expelled protons. I mean, I went up to him after this talk and I said, that's the most spectacularly interesting talk I've met in 10 years of going to conferences like this. Apologies to everyone here, because you've all given many talks that I've listened to. But it really was stunning.
Fourth phase of
David, look at YouTube, I can hint that. He's got introductory talks on the electric universe and Pollock. I've met him a couple of years ago and I've seen his work. He has changes on the interfaces of water, which I see as electrical interfaces, which we then use. We discussed this last year, remember, in the evening session. And there is something there. And on the it was, I think, already in the 30s they discovered that water in cells, has got this, what we call it, X-ray crystallography. They show that in living plants, I think, or living tissues, they show that these X-rays exist. This is as I say, 30s, and you see these 6 spots on it. They're very clearly.
I find this absolutely fascinating as well. Only one question: is Jerry with a J or a G?
G, Gerald.
Right.
Thank you. Gerald Pollock.
I'm in contact with a man in Kuala Lumpur.
Yeah.
I think it's Kuala Lumpur. He's in Malaysia.
Mm-hmm.
Who is the editor of the Journal of Neuroscience, or some kind of Journal of Neuroscience. And he's really interested in the very anomalous kinds of electrical excitations you get in water, in nerve cells, ionic waves of various kinds, polaritons forming. I still don't fully understand what a polariton is, but evidently you get these very well defined kinds of anomalous electrical excitations which can exist in circumstances which you describe. Now, how much they are due to interaction of the walls of the cells and fourth phase water and all the rest of it, I don't know, because it's not pure water.
Well, I know quite a lot about those things, because as Ollie said, physicists, it's the bread and butter, and there's a whole set of these quasi-particles that exist, and so if you want to talk about that at some later stage.
It's what happens when light passes through a medium, it becomes polaritons, not photons.
All right.
Yeah. Can you mention something here?
Lou?
I was wondering if you knew whether anyone had experimented with how states of water would affect the results of kymatics done with water. Kymatics is done with a plug of water. Kymatics. Cymatics. I'll explain. Let me define the term. You'll understand. You have a vessel with water in it, and you vibrate it, and you look at the nodal patterns of the water in the vessel. That's cymatics.
This is very old,
Is that PSI?
It's a coupling between a photon and an excitation state of material.
Yes, okay, fine.
That's what it is.
So you're looking at the global geometric structure that the water assumes under vibration.
But is this different from the normal
You've
ways
seen
you
clogging
experiment?
patterns where this is the same. Materials under vibration.
Yes,
Yeah.
absolutely. And that interacts with the light going through.
Well, you simply look at the surface of the water while it's vibrating.
Okay,
You
fine.
see beautiful patterns.
Oh,
if you
yes.
have notes or regular musical frequencies.
I think someone showed something like that at the conference.
But it occurred to me that what you see may depend on the state of the water itself.
That's very interesting. Brian Josephson did a very interesting show talking about Benveniste's work and then about water. And he did show what happens when you vibrate water in particular ways. And he showed that under different circumstances, you got completely different spectrum of excitations coming up. And he gave the reference to the work, and I can certainly get it from Brian's. Is that something you'd like to find out more about?
I
Good.
think the whole group would like to find more out about this.
Yeah. But, I mean, that's completely different from my concern, I thought. But if you tell me that the structure of the polymolecules might give rise to different things like that, I'll think about it. Okay?
Okay, any more questions, comments?
Thanks, everyone.
Thank you, Alison. I particularly enjoyed this talk, and I think it's a format that we should take on more often. As you know, that's more to our members here. That half an hour talk and a half an hour discussion afterwards, instead of an hour talk and no discussion. Thank you, Alex.
Yes.
Unfortunately, okay, it's tea time.